So let's take it back a couple of weeks. We've talked about this, I think, or at least the last couple of weeks, time and time again. The linear model, which is, of course, something that we've been discussing over and over again, it makes a couple of assumptions, right? That the items that go into it have an effect on the outcome of the model itself, right? So remember, temperatures go up, or rather ice cream sales go up, robberies and crime go up, right? Right, that's that additivity. Also, we assume linearity, which means that if we sell one ice cream cone, one person's house gets robbed. If we sold 200 ice cream cones, we expect 200 people's houses to get robbed, right? I'm just making this up, but you see what I mean? Like, there's a linear effect. If we had the assumption of exponentiality, then we would expect an exponential rise with every single increment increase in whatever our predictor is, right? If it was ice cream, if we sold one ice cream cone, then we would see maybe one house break-in. If we sold 2 ice cream cones, then we would maybe expect to see 5 break-ins, right? That's more of an exponential relationship. In the linear model, we expect it to be a vertical, whatever, diagonal, sorry, can't use the words. We expect a diagonal line. A diagonal line has a slope of 1, right? Do y'all remember that? A slope of 0 is a horizontal line. That's no relationship, right? Okay, so we expect our values and our variables to be additive, and we expect them to have a linear relationship with each other. We also expect there to be independent of errors. So anything that could negatively affect the model, we expect it to be independent of those things. No factors that would relate to it would relate to it. We've also talked about homoscedasticity, right? The ability for items to be generally correlated with each other. And then the normal distribution of the errors. We talked about that a few weeks ago too, where we talk about a normal distribution, right? This big normal distribution. It's not necessarily the normal distribution of GPA, but rather the error or the deviations from the mean are normally distributed, right? So we have generally a normal distribution of the variation away from whatever the average is. Now, all of those, you should know, we've talked about them many times before. This week, and that's the reason, I don't know if you can tell, but that's the reason they're in gray. They're kind of old. They're starting to collect some dust. This week, what I want you to know about the linear model and linear regression specifically is that we have a few more assumptions we need to make. Okay? There's a few more assumptions that need to be met in order for us to use this type of analysis. For example, the outcome, whatever the outcome variable is, whatever it is we're trying to predict, must be continuous. It must be a continuous variable, which means it needs to be quantitative, right? And continuous. So what's a continuous quantitative variable?
Do you mean like temperature?
Yeah, temperature. Good, that's one. What else? Think about your project. What's a continuous outcome there? Outcome. What's a continuous variable? Manta and Ken. I think this is y'all's project topic, isn't it?
Yes, I think wind speed.
Wind speed. Okay. Okay. Good. Yeah, it could be 5 miles an hour, 15 miles an hour. And I've been in plenty of hurricanes, y'all. I've been in wind speeds in excess of 95 miles an hour before, standing barely, but yep. Good. Good. Manta, do you have any?
Not regarding this, but I think is income and age.
Yeah, income. Yeah, income is an outcome variable that's continuous, right? You can have an income all the way down to zero. If you ask Donald Trump, you might have an income that's in the negative territory, right? I know lots of people who report negative incomes on their tax returns. But yeah, it's continuous, right? All the way one area of the spectrum to another. Now, that is talking about the outcome variable. It must be continuous. It cannot be categorical, okay? Must be continuous. Each predictor must be either continuous or categorical. And if a predictor variable is categorical, it must have at least two categories, okay? At least two categories. So what's a predictor? What's a predictor of income? Hint, hint, nudge, nudge. We talked about it last week.
Educational attainment.
Educational attainment. What is educational attainment? Not Kara. What is educational attainment? Which one of these types of predictors is it? Continuous or categorical?
Would it be considered categorical?
Yep, categorical. Because, Juliana, if I told you that my educational attainment was a master's degree, and you said, oh, great, I've got a bachelor's degree. Well, even though educational attainment can be considered ordinal, because there is an implied order, right? High school diploma, certificate, associate's degree, bachelor's degree, master's degree, doctoral degree, right? There's an implied order, but we can't assume that the distance between each of those educational attainment categories is meaningful. We can't assume that the distance between them is the same or meaningful. So let's think about this. What's the distance between high school diploma and associate's degree? Think distance as in time.
Isn't it traditionally like 2 years?
Yeah, 2 years. Good, perfect. What's the distance between an associate's degree and a bachelor's degree?
2 years.
Okay. What's the distance between a bachelor's degree and a master's degree?
Two.
Sorry, I heard something. I couldn't understand.
I said 2, correct? Right now.
2 years. It depends. It depends. I know a master's degree in counseling is like 3 years. But generally, most master's degrees are either 1, 2, or 3 years. MBAs, for example, are 1 year generally. But here's the thing. What's the distance between high school diploma and a certificate of whatever, proficiency or technical certificate? For us in Arkansas, we have certificates of proficiency that are generally less than 30 hours at the undergraduate level. Technical certificates are generally 31 to 59 hours. So the distance in terms of years is considered about less than 1 year and essentially 1 year and a half. Here's the thing though, that's not how all other continuous data work, right? Because it depends on where you are and how long it takes you to complete your degree, right? So we don't think of educational attainment as continuous, even though it does have an implied order. It's definitely not a continuous variable because we don't have everyone on the same cohort model, and we're not pushing everyone through year by year by year, right? If only education was that efficient, right? But I mean, gosh, my wife, she finished her associate's degree before we got married, and now she's working on a bachelor's again because we're finally in a place where she felt like she could work and do it. So I'm proud of her, but there's definitely not equal distances between those ordinal categories, which is why it's not continuous. Does that make sense, Juliana?
Yes, it does.
Okay, so yeah, so good. Educational attainment, categorical. What's a continuous predictor of income? What would we consider a continuous predictor of income?
Maybe age.
Good. I didn't say not Kara, didn't I?
Sorry.
No, that's I'm just messing with you. But no, age is great. People generally earn more the older that they are, up until a certain threshold of about 50. Once you get to 50, people who are making a lot of money at the age of about 50, they continue to make a lot of money and probably even more money. But depending on where you are at 50, there's generally not a lot of wiggle room. That's what we've learned with income in the U.S. Because people start to draw down and retire and make Social Security and all that kind of stuff. So yeah, so age to a certain extent, right? If you want to cap it at a certain threshold. But yeah, good. So that's one. Also, for part-time workers, if we are only analyzing income for part-time workers, the number of hours you work, right? If you're paid hourly, guess what? You work more hours, you get paid more, right? So that's what we mean by predictors, both continuous or categorical. This next bullet is called non-zero variance. What in the heck do I mean by non-zero variance? By the way, this is all in your textbook, y'all. Make sure you read before class too, okay? Oh, and Manta, sorry, I just saw your chat box. Yeah, IQ, it could be a predictor, right? Don't know, let's see. I know some very smart people who make some really dumb choices as far as, you know, what they want to do and everything. So, but no, definitely an IQ is a continuous variable. And for the most part, I think many people would argue that, yeah, that could be a predictor of income. But going back now to non-zero variance, what we mean by non-zero variance is that in order to have predictors predict an outcome, all the predictor variables have to be different in some way. They have to vary, right? If, let's just say, I wanted to predict, the number of hours of sleep that we all get, okay? Anybody want to testify as to how many hours of sleep they typically get a night?
I get around 7.
You get, oh gosh, hush it. Like, y'all are gonna make me so jealous. I get about 4 or 5. But let's just say I get 4 or 5. Kara gets 7, whatever. Ken, I'm gonna make the assumption, or just you know, guess here. I'm gonna say that you get 4 or 5. Juliana, I'm gonna say you get 6. Manta, I'm gonna say you get 4 or 5. You know, just throwing numbers out here. That is variation, right? Kara gets 7. Eric gets less than 5. Rodney gets 12. I don't know. I'm just messing with you. But you see what I mean?
Sound about right. I
So
need
you know
my
what I'm
beauty
saying?
rest.
Well, some people just are efficient sleepers. Let me tell you, Delaney, she lays in bed within 5 minutes, done, gone, out. And I'm just like, I'm barely done with my second hand of euchre because I have to play card games to go to sleep. So, everyone varies in a lot of different ways. So what if we were trying to predict happiness amongst this class? And let's just say my happiness level was a 1, Kara's was a 5, Rodney's was a 10, Ken and Manta and Juliana were somewhere between 4 and 7, right? Then we know that the outcomes vary, right? The outcomes vary. But what if we all got the same amount of sleep? What if every night we all got 7 hours of sleep? What's the predictive power of sleep on happiness? How much variance do we have in our predictor variables if all of us get 7 hours of sleep?
0, right? Right.
No, yeah, right. Rodney, you're right. Exactly. 0 is the variation because the mean, if all of us get 7 hours of sleep, and I'm like pointing down at all of y'all are all on this little Brady Bunch thing. The mean is 7, right? The average hours of sleep is 7. Well, I don't have any deviation from the mean because I get 7 hours of sleep. Kara doesn't have any deviation from the mean because she gets 7 hours of sleep. Juliana, Ken, Manta, Rodney, all of y'all, no one deviates from the mean. Guess what that means? Our variance is 0. And when variance is 0, how much can the average, or how much can the hours of sleep that we get predict our happiness as a group? It can't.
7.
What did you say, Rodney?
Can you repeat the question? Because I thought I said
Oh, yeah.
7, but I had to make
Oh,
sure.
yeah. No, the question was if all of us have 0 variance, right? If all of us have 7 hours of sleep, the average number of hours of sleep for the class is 7. All of us have 7 hours, which means there's absolutely 0 variation. How much can number of hours of sleep predict our very different happiness levels, right? We all know we're happy or less happy based on a certain scale. If we don't have any variation in our sleep pattern, sleep is not a predictor. Not at all a predictor, right? So that's why we have to have non-zero variance. We have to have predictor variables that vary from the average. Make sense? Does that make sense, y'all? This has 2.5 bars, right? See that? That means I need for it to make sense before I move on.
It makes sense.
Okay, good. Now the last one, no perfect multicollinearity. Okay, say that out loud. You don't have to unmute, but just say it out loud. Get it out of your system as an idea. What we mean by multicollinearity is that as one predictor changes, another predictor changes. Okay. So what if we try to predict happiness in 2 ways? Hours of sleep and number of calories that we ingest, right? Number of calories that we take in at night for dinner. Well, if we got 7 hours of sleep, I wish, last night, and we ingested 500 calories for dinner, and then tonight we get 14 hours of sleep, or maybe someone else gets 14 hours of sleep, Ratane, and she ingests 1,000 calories. Well, that's called multicollinearity, because if her, essentially where I am in terms of my calories and my hours of sleep and her calories and her hours of sleep, essentially as mine double, hers double, well, then it really doesn't necessarily have any impact individually on the number of hours of sleep. We understand that multicollinearity exists, right? Remember how I gave you the example a long time ago about studying for the ACT? and I said hours of sleep the night before, having a good breakfast in the morning of, studying up until, the exam, all those sorts of things are good predictors. Well, hopefully they wouldn't be all the same strength of a predictor, because when two predictors or more are all have the same strength and the same effect on an outcome variable, it's hard to determine which ones are really predicting the outcome best. Okay, does that make sense? So we're going to have multiple collinearity. We're going to have predictors that are moving in the same sort of direction. However, we don't want it to be perfect. We want it to have some sort of differences at certain points in times. And so this is, again, these are the 4 additional assumptions for linear regression, Ken and Mamta. Okay? Hint, hint, nudge, nudge. And Mamta, you said 2 hours. Goodness gracious. I should end class early so you can get some more sleep, right?
Yeah, that's what I get usually.
That would be great. Then I have the 14 hours.
Can't win for losing with y'all. Man, y'all are hitting me hard tonight. So the linear model actually uses some pretty simple math that you learned probably in 7th or 8th grade. Does everybody remember how to plot lines on a chart, like on a graph? Remember the y and the x-axis and the intercept and the slope, right? Remember those things? Y equals mx plus b. I probably should have had it tattooed somewhere. B being the intercept, right? The intercept itself, and m being the slope that affects where it lies along the x-axis. So if we have a single predictor, in a linear model, that is the equation that we're creating. So, for example, there it is. Let's just say that we are trying to predict, again, happiness, right? If we know that the intercept is like 1192, essentially it's just simple math. 1192 plus the multiplication of 393.8 times 50, whatever those may be, right? X is generally the predictor itself. So a model would take into account how X interacts with Y, and it would create the intercept and the slope. And so we would have, of course, a Y variable and an X variable, outcome and predictor. And a linear model is going to help us determine what is the intercept and what is the slope. Okay? Okay. If we have multiple predictors, don't be scared. It's just 2 predictor variables, each with their own slope, right? M1 and M2. Slope 1, slope 2. And again, pretty simple math, but sometimes people think it gets a little complicated. Again, it's really not that hard. I'm just trying to show it to you in a mathematical format here. So what we would do then is multiply our slopes and our x values, and then add them all together. Again, remember how we talked about a linear model is additive, right? Additive, yeah. See it now? See how it's additive? We are adding it all together to equal y. You can have negative values, of course, negative intercepts, which then reduce the outcome variable. I wanted to, again, show you a pretty good flow chart. You might get a little lost in it, but this comes, again, straight from the book. In order to do a linear model fit and fitting the linear model, you really need to understand what we are looking at in terms of our assumptions being made, any kind of potential graphs that we want to do, and then where we make assumptions and they're met, and then how do we generalize from there. So here you can see the initial checks, right? That means that we are looking for linearity, maybe some outliers. We can do scatter plots, we can do PP plots, right, to test for linearity. If we don't have linearity, then we may need to transform the data. We may need to remove the outliers, right? Go back and double check, make sure all of our data are correct. And then once that's done, we can run an initial regression and save our diagnostics. That's a step that we're not going to worry about too much right now, because those diagnostics aren't necessary really for us in the long run, the scope of what we're really trying to do. So instead, we're going to go straight into looking at our assumptions, right? Linearity, homoscedasticity, and the independence of variation. And then, of course, normality being charted out by a histogram. What you can do to check for linearity, homoscedasticity, and independence of observation is to graph the predicted z-values versus what we call the residual z-values, okay? And once you're done with this, say, okay, assumptions are met, then let's go in and look at our model itself. And of course, we can then run it and generalize the model. A couple of other steps here. If we did not have normality or lacked independence, some options for how to handle it. Again, I don't want you to necessarily worry about that tonight. I want to do kind of a simple linear model and a multiple linear model for you. We're not going to go too deep into the what ifs down here at the bottom, okay? All right, so I've given you an example data set. Go ahead and download that from Canvas if you have not already downloaded it. That data set is insurance costs. Insurance costs. This is the one thing I think we all hate to do, but in the end, when you need it, right? Insurance premiums are very expensive, especially health insurance. And so I've got a downloaded data. I downloaded a data set that looks at insurance premiums. So here in the data, we've got just a couple of variables. We have the age of our participants in the plan. We have their sex, female or male. We have their body mass index, which, does everybody know what the body mass index is? Does anybody not know what the body mass index is? I'll make the assumption you know, but for those who might not, the BMI is a combination of weight and height that determines whether or not you may be on some sort of scale of obesity. And so generally, the higher the BMI, the more likely you are to be in that obese range and thus have you know, maybe more difficult health problems. Yeah, here.
Was it this class where did you give us the podcast to listen to that talked about normal and how it was established and BMI and how it's fully affected by the non-normal normal that was assumed back in like the 20s or something? Okay.
Yeah, yep. I also gave you the one about temperature. Yeah, so there's two. Yep, good. Yep, so BMI, really not that great, but nonetheless, it works sometimes. I was 15 years old and I did a little internship on a military base, and my friend's mom kind of worked on the base too somewhere else. And one day we went over to her office and she was in like the wellness area, and she had these like tongs, and she would pinch my skin. And I never knew like the military was so precise about that kind of stuff. Kara, do you know what I'm talking about? I just saw your reaction. What are those things, and why did it make me feel bad?
They're terrible. They used to do that at the gym. If you'd go in and hire a personal trainer, they would use those little pinchers and grab the back of your arm.
Yeah, man, you can grab my entire arm with those things. It's not. I have no muscle, but you know that's what clicking all day does. So anyway, so then we've got the number of children, right? The number of dependent children, whether or not this person is a smoker, where they live, what region, and how much I believe this is annual premiums. Yeah, annual premiums for their healthcare. So how much do they actually have to pay out of pocket for healthcare, right? So this is something that's real. I mean, this is real, y'all. This is something that people deal with all the time, right? You want to talk about actuarial science? They are looking at so many more variables than just these. Do you all, hey, by the way, speaking of predictor variables, do you know what's most predictive of how much your car insurance is going to be?
Just a wild guess, but is it your gender?
Keep trying. Close. I mean, no, yeah. I mean, generally, I think males tend to pay a little bit more than females because we like to show off sometimes, but no, not necessarily. There are actually two factors. And I'll go ahead and knock one out for you. One, are you less than 25 years old? Right? Younger drivers tend to be very expensive, but regardless of your age, what is another predictor?
I feel like it's the type of vehicle you're driving.
Sometimes.
Yeah, it
A little
also
bit,
depends
yeah,
on
but
if
not
it's,
much as something else. What you got? Sorry.
I'm sorry. I think it also depends on if the vehicle is new or old.
New or old, right? New car, old car, yeah. But think about all the people that have the new cars, all the people that have the old cars. They tend to cancel each other out. There's one factor that tends to determine your car insurance premiums more than that, regardless of whether you have a new car or an old car. Do y'all know what it is? I can tell you what mine is. Mine is 72223. Do you know what that is?
That's your zip code, I'm assuming.
That's my zip code. Does anybody else want to divulge their zip code? I'm just joking. You don't have to. But seriously, zip codes tend to be indicative of broader traffic patterns. So I live in 72223, which means I generally have to drive 20 minutes to work because the majority of people that live out this far west in Little Rock generally either work in the next town over, which is Conway, or North Little Rock, downtown, whatever, closer to the hospitals, etc. We generally have to drive a little bit further. So just by the fact of me living in this zip code and all the other people that live in the zip code and the number of miles that we put on our cars, because nowadays insurance companies know that kind of stuff, right? It's more expensive for me to be insured than it would be if I lived like a mile from my office, or so to speak. So yeah, look at it, look it up. Zip codes are generally how traffic, car insurance premiums are generally set. They
I
know
know.
how many accidents happen. Oh, go ahead, Roger.
I was gonna say I do notice that, but they do offer a lot. Well, depending on who you're insured with, they do offer incentives for like students, or if you take a defensive driver's course, or possibly faculty and staff, I believe. And if you work from home, you can also tell them that, and they could help you out with your deductible.
Right. No, there's lots of discounts out there, but overwhelmingly, we're starting to see a focus on zip codes still, right? Lots
Yeah.
of. Yeah. Let me tell you, I never thought I'd see this in my life. I got a check from my car insurance company last year. Did anybody else? Yeah. Kara says yeah.
Yeah, Geico.
Yeah, because guess what? People weren't driving. There was no. I mean, I thought that was the responsible thing to do. Here's the deal, though. I wish they would have reimbursed me for at least half of my premium. They didn't do that, but the fact that they cut me a check and I cashed it means I have absolutely no claims to that money that I gave them that they did keep, right? So it is what it is. Anyway, so here's our data, right? We're going to look at insurance costs. We're going to look at predictors of higher healthcare charges. So what I want you to do is let's go out and close that. Let's see. There we go. Oporto. Gosh, it reset. Dang it. Here we go. Launch it again. It should only take a sec, hopefully. Hey, Rottene, did you ever figure out how to get data out of Oporto? I meant to ask you that. Sorry, earlier.
Nah. Well, actually, it's not funny, but no.
Okay. I'm going to show you just since we're out here live with everybody, just so everybody can see. If you are ever in Oporto and you need to bring data back to your computer, right, to your desktop, you need to be able to get it out essentially of Oporto. And the only way I know how to do it, here it comes. There we go. The only way I know how to do it, y'all, is the opposite of when we upload a data file to Oporto. So notice that I've got, here's that insurance file right here, right? There's our insurance file. So here's the insurance. If I wanted to bring insurance back to my computer, well, that's odd. It usually allows me to click on these clouds. Rottene, were you not allowed? Oh, it's still connecting. Okay. Maybe it'll be there in a second. Basically, this little down arrow cloud, when you click it, you should be able to save any of these files onto your personal machine. So we'll come back and check on that in a little bit. All right, so coming back up to desktop, let's see, insurance. Okay. So here we go. I've first just run essentially a correlation of BMI. I'm looking at body mass index and insurance charges. So here, this correlation looks sort of kind of linear, right? Kind of like as your BMI gets higher, right? As your BMI increases, your body mass index increases, generally, it looks like your insurance charges also increase. There are some that have high BMIs that have pretty low insurance charges also, but overall, it's something to start with, right? Notice that the correlation provides us with an R squared. Does everybody remember what R squared means?
Isn't it the Pearson correlation square? Or
It is, yeah. But what does it tell us, Rottene?
the estimate of the predictive power of the variant?
That's exactly right. How much variation is explained by that one predictor, right? So with a 0.039 R squared value, that tells us that about 4% of the variation in the outcome is explained by the BMI as a predictor variable. Good job. So now that we're in SPSS and we have the data file loaded, I want to show you first that the original data file had values for smoker and values for sex that didn't really fit well. So originally there were yes and no, and then smoker was also, let's find it. Yep, smoker was yes and no, and sex was male, female. I recoded them, right? Like we do in SPSS. I went to data and I recoded or transform and then recoded into different variables. And I gave them these categories of 1 and 0 for yes and no, and then 1 and 2 for male and female, okay? So I'm gonna use the BMI, right? BMI is a continuous variable. Can everyone agree to that? Cool. So BMI is our continuous predictor. And then I'm interested in understanding if being a smoker affects your insurance premiums. So we've got smoker recoded as two numeric categories for SPSS purposes. So first thing I want to do is I want to run what's called a forced entry model, And what this means is that I'm going to just do a single predictor. So under regression, linear regression, I'm going to include just BMI as the independent, and the charges for health insurance as dependent, okay? Under statistics, we can do the descriptives, we can do the collinearity diagnostics, and then under plots, remember how we did Z predictor, Z residual, right? Remember how I told you about that a couple of slides ago? There it is. Looking at linearity, homoscedasticity, and independence of observations. Z predictor versus Z residual. Pretty easy stuff once you get in here and you see it as a SPSS option, right? You can also do a normal probability plot. You know, it's pretty straightforward. Now, also on this prior slide, it asked us if we wanted to save our diagnostics, right? If we were going to save our diagnostics, well, then we would do that under save, right? So we would find the standardized predicted values here, and we would save them. We could also save our standardized residuals. If we were looking at Cook's distance or anything like this, which is for another time, but definitely just wanted to show you what save means. Under options, we're using the probability, the alpha value of 0.05, right? Because we want to have 95% confidence that this relationship wouldn't happen at random, okay? And then hit continue, and then you can either hit paste or okay. I'll just hit okay. And here we go. The first thing we see on our linear regression is the descriptive statistics. So look at that. The average BMI is about a 30.6. The average charges for healthcare is about $13,000. Look at this though. The standard deviation is $12,000. That means there's a lot of variation from person to person in terms of how much they get charged. BMI, the difference is actually kind of pretty big too, which means, you know, generally there's a decent amount of variation in BMI. But man, 12,000 is almost the same as the mean. That's crazy. That's pretty big. So remember how earlier we talked about non-zero variance with our predictors? A BMI with standard deviation of 6, that's evidence of non-zero variance. If the standard deviation was close to 0, I'd be a little bit worried, right? Okay, so then we look at our correlations. You did correlations last week. You know what correlations mean. The correlation between BMI and healthcare charges, look at that. It's 0.000 significant. The correlation itself is a 0.198. What does a 0.198 correlation mean? What is a 0.198 correlation? Is it less than 3 or 0.3?
Yes, it's a
Is it
weak
less?
correlation.
It is a weak correlation, Rossini. Yep. So we've got a weak correlation here, but still it is determined to be statistically significant, right? At the 0.05 level. Its p-value is less than 0.001. So we know that it's a significant predictor, even though it is a weak relationship. Make sense, y'all? So that's just looking at the correlation. Let's look at what the model says. Remember how earlier when we plotted it on the correlate, we plotted the correlation. remember how we had that R square value? What was that R square value on that plot? Oops, sorry, wrong way. There it is. What's the R squared value on that plot? When we plotted BMI versus charges.
.039.
0.039. What do we see here in our linear regression model summary? Anybody?
It's the same.
The same, right? Watch out. Okay. The cat wants to learn about linear regression, right? All right, cool. So yeah, so like we would expect, right? The same R squared value, we're doing the same darn thing up until this point. We are looking at the correlation in order to determine the R squared values and those sorts of things. Now, the linear regression model does one additional step, which it does an analysis of variance, which then tells us if the overall model is significant. Up here at the beginning, we simply looked at whether or not the correlation between two variables were significantly different. And down here, we're looking at this overall model step. So if we had more than one predictor, this is where we would see each model showing us if it was statistically significant or a significant predictor of the outcome. So having only one predictor, we do see that it is statistically significant, right? It is a significant predictor. And so what we then look at are our coefficients. We look at our coefficients, okay? And here, this is where we get the understanding of whether or not, again, BMI is a significant predictor. There it is, right? 0.0000. But also, this coefficients table is where we find that equation. Remember how I told you before, we need the intercept and we need the slope and value for x in order to predict y, okay? We need the slope, the intercept, and the value of x to predict y. Let's come back and look at it. What's our slope, y'all? What's our slope? Anybody know? Anyone want to guess?
I'm just gonna stab in the dark. It's not 0.198, right?
Where do you see 0.198?
I'm moving my mouse on the screen, which is not helpful. The standard, oh, I'm looking in the wrong table. I was looking under coefficients.
Right here? You mean this standardized coefficients data?
Yeah, that's not it, correct?
That's not it.
Okay, great.
Close. It's the unstandardized data. It's the 393. Okay, it's the 393.873. That is the slope for BMI. So 393.873 times, if my BMI was 30, right? Then plus the intercept, would equal my healthcare costs, or could equal my healthcare costs, right? So what's the intercept?
Is it T?
Was it what?
Is it 7.397?
Close, but not really. It's the constant under unstandardized beta. Constant under unstandardized beta. So it's 1192. P is the measurement of the model itself, Kara. And so the T value is whether it helps us to determine whether or not the model itself is significant. Are you double checking my math?
No, I'm just trying to go back to where it was in the book to see what I maybe didn't absorb, because I remember looking at something similar in here.
Hey, by the way, y'all keep Julianne in your thoughts. She just lost power. Okay, so this is one predictor, right? One predictor. We also have our charts. Oh goodness. that does not look like normality to me, right? Lots of distance there between the lines. So remember though, the R squared value here is 0.039. We're talking about 4% of variation. I wouldn't hang my hat on BMI being a good predictor of healthcare costs, right? I wouldn't necessarily do that. So sometimes we have to do what's called multiple linear regression, where we include 2 or more predictors, right? So remember how earlier I said I want to do smoking, whether or not someone's a smoker, and whether or not they have a high BMI, low BMI, that sort of thing. Now, coming back, oops, there we go. Coming back, remember I told you that there's 2 ways of ordering predictors in the model. Forced entry puts all predictors in at one time. So under forced entry, we've got in block 1, BMI as a predictor, and we can also put smoking. Oops, smoking recode, sorry. Smoker recode as a predictor, right? That's forced entry. If we didn't want to do forced entry, we could do stepwise. And that's what essentially it sounds like, where you create one step with one predictor, step 2 with both predictors, right? Step 3 with 3 predictors, right? That sort of thing. So all you have to do for stepwise is to just go to next and then put in again BMI and smoker recode. And that way you can see how your model changes as you add more predictors. So I believe under statistics, R squared change was an option we didn't select before. We can select it now because we expect the R squared value to change as we put more predictors into the model. Okay? And so hit OK. And now we've got a new model. Notice, however, initially the correlations are here. BMI is correlated with charges at 0.198, like it was before. Yep, 198, same thing now. Now, when I included whether or not someone was a smoker, how would you classify that correlation? 0.787.
That's a strong correlation.
That is a strong correlation. I should have changed the variable from smoker to people who drink Coca-Cola.
Atlanta.
So, yeah,
right?
I thought. Yeah, I got you. My wife's the same. I mess with her all the time. She drinks Coca-Cola too. I drink. Do y'all know what I drink during class? Have y'all ever wondered what in the world this is?
It looks like you're drinking milk.
Yeah, I drink about a half gallon of milk every class. Every, I'm literally like 3 hours of me talking. I'm just sitting there trying to milk. Anyway, so now we see that smoking has a pretty high correlation with healthcare charges. But remember, smoking is just a unit, like basically a yes or a no, right? So it is limited. It's definitely not a continuous variable, but yet we can still see it does have a pretty high correlation with healthcare charges. Both of these variables, again, we knew BMI was statistically significant, but now we also see that smoking is statistically significant also. So where's our standard deviation, right? We shouldn't expect much out of a mean for smoking because it's meaningless, right? When you have a categorical variable, there is no mean. That's like saying, what's the average educational attainment? Half a bachelor's degree? I don't know. You know, so don't pay too much attention to these here if it's a categorical variable, but pay attention to them if they're continuous. Okay. So here we go. At step 1, we entered the BMI variable. At step 2, we entered the smoking variable, right? So check out our model summary area. Remember before, our R-square was only 0.039? R-square with smoking included? What does that mean? What does that mean, Neil? Instead of explaining 4% of the variation in healthcare charges, we now explain, fill in the blank. %4 versus
It's 66%.
66% of the variation in healthcare charges can be explained through the use of 2 predictor variables, smoking and BMI. Now you may wonder, what's this adjusted R-squared here? Adjusted R-squared is simply a more conservative estimate of the R-squared value. Some people use it, some people don't. I tend to look at it to see if it differs very much from the R-squared. If the adjusted R-squared is a lot lower, then that gives me reasons to be cautious about what I'm looking at in terms of the R-squared itself. But this one's really close, 0.658, 0.657. I'm good with it. So now let's look at our ANOVA section where we have the 2 models. Well, model 1 was statistically significant. It has an F value of 54, which is like a T value, but for an analysis of variation between the predictors and the outcome. Well, when we add in smoking in model 2, that F value jumps way up to 1,283. Still very statistically significant. So what does that mean, though? What does that mean? What we want to do is we want to look at our individual models and say, okay, BMI, smoker recode, we understand that both of these are statistically significant predictors, but one definitely has a pretty large impact on the model. One definitely has a pretty large impact on the model. So what we have here is, again, the T value showing them both to be significant. And notice that down here, now that we have 2 steps, we also have a section called excluded variables. This just tells me that in model 1, we didn't include the smokers, right? Which is what we wanted. So when you look at collinearity diagnostics, what we want to see is generally that these don't overlap, right? So in model 1, they are not overlapping, right? See how they're very different. Model 2, they're both very different again. So that's good that they don't overlap. When we look at the charts, look at it now. Look at that now. the variation between them shows a much more of a linear predicted relationship, right? Before, remember when it was just BMI, it had that big gap in it. But the combination of BMI and smoking has really created a much more of a linear predictability. And then that's it. So now we've got the coefficients. And the coefficients are where we find the slope and the predictor variables, right? You all ready to write some equations? I'm going to give you 20 minutes in a breakout room. And I'll come in and share my screen. Actually, no, I'll just give y'all 20 minutes and I'll just mute my stuff. Give you 20 minutes. Y'all work on this for 10, take 10 minutes for a break, okay? All 4 of you, I expect to be talking to each other, trying to figure this out, all right? So, does everybody have the outcome of the, here, let me do something real quick. I will take a screenshot, upload it with what I want you to fill in, okay? Not my fingers, goodness gracious, look at that finger right there, like that's ridiculous. All right, take the screenshot. I'm gonna save it, upload it for you, and then, okay. And so now everybody should be able to access it in the chat in just a second. All right, there we go. It's a JPEG. So what I'm going to do is come back to the outcome so you can all see it, okay? Did everybody get the picture? Slide on it? Good deal. What I want you to do is I want you to use the second model, the one with both predictors, okay? Use the second model. Tell me whether blank and blank could significantly predict blank. So what are the inputs? What are the predictors? What is the outcome, right? And then fill in all of the blanks. All right, 10 minutes and then take a break. I've got 28 after, we'll come back at 48 after, okay?
Hey, y'all.
Hey, where's the screenshot that you just took?
It's in the chat.
Okay.
Anybody want to take a stab at the first one?
I don't know how to do it.
Oh, so did you see the screenshot that he?
Yes.
Yeah, so we just need to fill in the blanks. So that first one, we just have to basically say the predictor variables and the outcome variable.
Okay.
So it's just what are the 2 predictor variables that we put in? So those were BMI and smoking status, right?
Yes.
Yeah, I
I
also
said it on-
Cute, Manta.
You heard me?
I didn't hear you, Nay. What'd you say?
I was letting them know that it says it like the predictors, the constant BMI is on B, and C, it says predictors, constant BMI smoking.
Yeah. Yeah, so those are our two variables were BMI and smoking status, and then those significantly predict a participant's charges.
I think,
Yeah, so that's the first one.
yeah. I'm sorry about my son.
Oh my gosh, don't even worry, Mamta. I'm sure you saw my dog attack my cat like just 5 minutes ago. So no, kids are not a problem. Okay, so this next part is going to be tricky for me.
The multiple regression part.
Well, just which piece of the table is the piece that we want? I get a little bit lost sometimes in these tables. So the results of the regression indicate that the model explains some percent of the variance. So is that the R squared, you guys?
Is the answer in the screen sharing screen, or should we analyze?
Oh, no, I think it's in this table of coefficients that
Oh,
Eric
okay.
left up. Yeah.
I think that's R square.
So is that the standardized coefficient beta? Or is that, it's not T, right?
No, I think in previous you said it's not T. I'm confused.
Hold on, hold on.
Mm,
Looking. Bootstrap around coefficient. Okay. I'm just digging through the book real quick to see if I can remember where we talked about it. Shoot. Okay. I'm gonna guess that it's the standardized coefficient beta right in the middle, and that it's, oh geez. That can't be right. Thanks, Eric.
Are we going to do math about the percentage, or I don't know?
No, I'm pretty sure it's just a number that we're gonna pull out of these tables.
Okay.
Yeah, so like we just have to find the percentage, and then we get to say if it's a strong predictor of such and such with the F value of whatever and a P value of whatever. So I'm pretty sure we're looking at model 2, right? Where we had both of our predictor values.
Uh-huh.
And
Is it coefficients beta?
that's my guess. But then which one do we pick?
I was thinking it was the where it says the unstandardized coefficient part.
Right. But those numbers are so big. Right. We can't have 388% variance.
True.
Maybe we
So
can.
what? I don't know. So what if we just pick the beta data and then move on to the next question?
Sure. So are you thinking like 79% based on 0.787, Ken? Is that what you're thinking?
Yes.
Okay. Sure. So then that makes the model, what kind of a predictor do you want to say?
strong.
Yeah, yeah, I think. Oh, yes, that, yeah. So it's a strong predictor of charges. I think that's what would go next. And then F, so what do you guys see how it says F parenthesis something comma something?
Mhm.
Do you think that means, like, do you think that's two different values or do you think that's two different words?
Hmm.
Like,
I
is
think
it,
that's two different values, and that might be some kind of coordinate. I don't know.
well, I mean, if you look at the ANOVA table, the F values are for model 1, 54.709. But for model 2, which is the one I think we're supposed to be looking at, it's 1283.923.
Is
You
it
guys-
both or
Well,
I don't know.
I think the F value is 1283. Do you guys see anything else on here?
Yeah,
Okay.
I also see just the bottom one, but what we write after the comma.
That's the part that I don't know. Like, I think I'm just gonna, so F
Maybe-
of blanks equals 1283.
Also for residual, it's not given, so I think it's blank. Like, I don't know. I'm just predicting here.
Right? My guess is that's it's got our two variables in there, but I have no idea.
Maybe 2F.
What do you mean? I don't know what you mean, Ken.
Like the first comma before the comma is 1F and behind, and then after the comma is another F, or just 1F.
Oh,
I'm not sure. I'm just guessing.
I'm guessing just one F because
Uh-huh.
then I'll just say this. I'm only thinking about model number 2. I'm just not even looking
Okay.
at the numbers for model 1. But if you guys think we should, we totally can.
So if it's only 1F, maybe after the comma is 923.
Oh, I see what
Or-
you're saying.
Yeah. I don't know.
Yeah. Well, let's move on to P and we'll just see what
Okay.
happens. So P is, that's the significance, right?
Yes.
Okay, well, that is the 0.0's business.
0.
Yeah.
Is that right?
Yeah, I think that's the one where if it's less than 0.01, it seems to always write out as 0.000.
So P is 0, 0, 0.
Yeah, with a point and it's like 0.00. I think that's, yeah.
Okay.
Okay, now we gotta find the B's. God bless it.
Module 2, right?
Oh God.
What did you say? Ken, did you say 102?
No. No. I think it's on standardized. Is that B, right?
Yes. Yeah.
And then
So
module 2.
yeah, that's right. So I guess
Uh-huh.
we would say for BMI, B equals 388.015, right?
Yes.
And then-
388.
Okay. And then P is less than, sorry, I'm just writing things down. I guess it's less than 0.01.
0.01. Where did you find the P? In the last.
It's the significance.
Oh, okay.
Yeah, so on the table, it shows us 0.000, but I think the way we write P is less than 0.05 or less than 0.01.
Okay, so less 0.01.
I think so. Yeah. And then for the smoker,
Is it 23593?
I think so, yeah.
Okay.
And then P is still less than 0.01. I think. Oh, God bless it. Oh, now we get to write the formula. Oh. All right, so
So the final predictive model, we have to do math.
yes. I think we just have to write the formula. I don't think we actually have to
Okay.
do that. lest we feel panicky. So I know that the two parentheses parts, those are our MX pieces.
MX, okay.
You know how it's Y equals MX plus B? So, and that's our slope. Which one did he say is the slope? Is that the coefficient of standard error?
I'm not sure.
I'm not sure.
Yeah, I think it's the standard error.
Okay, let's just go with that. Thank you, Mamta. So
Okay.
then,
I'm sorry.
oh no,
Oh, you're fine.
you're great, Mamta. Don't worry a stitch. So should we do the BMI first? So that would
Yeah,
be
okay.
31.787 times,
So what is that constant of B? I think it was something. I forgot, but I think we were talking about it previously.
Yeah. Do you mean B on the coefficients table or B in the linear equation?
B in the coefficients table.
Right.
I think we talked about it something. I forgot.
I think that's what we do the multiplication. So I think like inside one of the parentheses for BMI, it would be 31.787 times 388.015. I think. Do you guys want to go with that? Or I'm totally happy to go with something else if you get if that's way off.
No, I think that makes a little bit sense. Oh, no.
Hmm. Okay, so then what's the y-intercept variable on this? Is that t? I clearly want to use t for something, and I can't remember if that's completely wrong.
Yeah, I mean, we could just use T.
But then which one? So it must not be t, because which one would we use?
Are we still on the smoker or BMI?
Oh, well, I wrote down for BMI, I did the coefficient of standard error times unstandardized B, right?
Uh-huh.
And then for smoker recode, I did the same thing, standard error times unstandardized B. So those are the two parts that are inside the parentheses.
Okay.
But that the blank that comes before the parentheses, that's in math terms, that's our y-intercept, but I don't know which one of these variables that is. shoot, day noodle. Get 103. Oh, 134. Oh, is there something called a constant? It is. It's the constant. It's minus 3459, I think, you guys.
Oh,
Yeah,
so-
that's what I was
oh.
talking about. He talked something about the constant in B value, right?
Yeah, well, yeah, because I'm looking in here at one of the examples in the book, and it's y-intercept is the constant. So that must be then the minus 3459.
Okay.
So then what's y? What goes before the equal sign? Oh, I guess we just can figure that out.
We calculate it and then put the value.
Let's see what happens.
I don't know.
Oh, good Lord.
Are y'all on break?
Not yet. We're still doing the math.
Oh gosh. The math.
Now, did you want us to figure out why for the final predictive model?
No, there's no way to predict y unless you have an x.
Oh, geez. Okay, well, then we've done some
No, I
wrong.
wanted you to fill out the equation.
Just fill in the blanks, right?
Yeah.
Yeah. Well,
Yeah.
we had a crack at it.
see.
We'll see what happens.
All right, now 1 minute break.
Okay, I'm gonna run away. I'll be right back.
Okay. Hello.
Oh, I'm sorry.
All right, welcome back, everybody. I've got 48 after, which means we got less than 30 minutes till the end of class today. So no, don't apologize. Love hearing kids laugh. Makes me happy. Makes your heart happy. All right, so let's write the results. Who wants to read out bullet number 1? Each person take a different bullet. Doesn't that work out nicely? It's like I predicted that. So, who wants to take bullet number 1? Somebody's got to.
I'll go. Multiple regression was carried out to investigate whether BMI and smoking status could significantly predict participants' insurance charges.
Very good. Perfect. Bullet number 2. Somebody's got to do it. Who's going to do it?
The result of the regression indicated that the model explained 0.195 or 0.787% of the variance.
Before you go
Yeah.
further, Ken, what was
Okay.
the R squared for model number 2?
Let me see. Oh, it's gone. I forgot.
What was the R squared for model number 2? Here it is. Sorry, it's right there. Model summary. R squared for model number 2.
0.811.
I don't see 0.811 on here at all. Oh, I do. I see it. That's the R value. What's the R squared value?
R squared 0.658.
All right. Try it again.
So the model explained 0.658%.
Okay.
58% of the variance, and that the model was a strong predictor of charges.
Okay.
And
Perfect. Or
F,
significant predictor. Yeah, that works.
okay. And the F, I think is 1283.
1283. What about what about the figures in the F parentheses?
Figure, I don't know, 0.00.
Oh, no. So the F in the parentheses here, that is the model, right? The ANOVA model. You want to know
Yes.
how many predictors you have, and
Yes.
then subtract that from the degrees of freedom. Or I'm sorry, not subtract it, but incorporate the degrees of freedom. So we have 2 predictors, right?
Mm-hmm. Yes.
So it would be F2, comma, and then the degrees of freedom is 1335. You see that right here
1335. Yes.
in the
So
model summary,
the
1335.
okay. Oh, so the first blanket is F2 and the second one is 1335.
That's right.
Okay. And I know what okay. Equal to, I don't know what equal to.
So then we know what the F value is, right, for model 2, right here.
Yes.
So what is it equal to?
1283.923.
Good.
Okay.
Good. And what is P?
0.00.
You can just say less than 0.05, right?
Okay. Last. Okay.
Yeah, because I think the slide just has, the slide has a blank, right? So P is less than 0.05 or 0.01, right? Okay.
Okay.
All
Thank
right.
you.
Now, no problem. Good job. Next, who's going to tell us about the values of the individual predictors? So let's start with the first predictor. What was the first predictor?
I don't know, Eric, did you see that both Mamta and Ratane said they didn't write down the? Okay, I just want to make sure you could see their internet situation.
Yeah. Cool.
I think the first one is BMI.
Well, either one works, right?
Yeah.
which was a predictor, right? You can write them down however you want. BMI first or smoking first, doesn't matter. But we want to make sure that the beta weight is what the B value is called, the beta weight, and the P values match the predictor. So there you go. You said BMI, right?
Yeah. Yes.
What's the
And
beta weight for BMI?
I think B equal 388.
388, perfect. And what's the P value?
Less than 0.01.
Perfect. Yep. Good. And what's the next predictor?
The smoker.
And what's its beta weight?
23593.981.
Perfect. And what's its significance value?
Less than 0.01.
Great. Perfect.
Okay.
Both contributed significantly to the model, right? See that now? See how it's all coming together? So the final predictive model was healthcare premiums or healthcare costs is what you don't have to try to figure out what that equals right now, right? But healthcare costs are predicted by taking the intercept of the model plus the beta weight multiplied by the X value, right? Which is BMI plus the beta weight multiplied by whether or not someone's a smoker, right? There it is. Healthcare costs equal 1192.9 is the intercept,
Hey, Eric.
right? And the intercept, hey,
I can't,
the
so,
intercept is, oops, sorry, let me show everybody where the intercept is, Kara.
yeah,
Yeah, the constant, right? Constant. Actually, my intercept's wrong. I didn't update it. Sorry. The intercept's really -349. Or I'm sorry, 3459. My bad. I just put all these in while y'all were working. Here we go. -3459. So. All right, go ahead, Kara. Sorry. Muted.
I was just gonna say that on my screen, I can't actually see the final bullet.
Oh,
With the
you
filled
can't
in
see it.
values. Yeah, and I didn't know if that was just me or if other people also can't see it.
Oh no. What do I do? How about this? Is that better?
No, it just doesn't show up. I don't know what to fix on my screen either.
What do you see? What's
I
the
can see
final
the-
bullet?
Well, here I can see it, but on the other screen, I can just see the tops of the letters.
The final predictive model?
Yeah, I can see
you
just
see-
the top half of it. The whole bottom of the slide is kind of cut off.
Oh gosh. Still?
I can see healthcare costs now.
Oh gosh. Okay, here, we'll just keep it here. Is
Okay.
that better?
Yeah. Oh,
Okay.
so
So-
no, this is really helpful because we got confused on that last bullet. Well, I was super confused and probably driving the confusion.
Normally it's not my job.
So the X is not in that table. We were just supposed to put BMI or smoking.
Right, because we haven't filled it in yet. We're really trying to create the equation, not solve the equation.
Right.
Okay, creating the equation structure versus solving the equation. But I tell you what, y'all, let's do it. Let's have fun. If we can't invent such a thing, right?
Is the X value in that table?
In what table? This table? Or this
No,
table?
no, the SPS
This
says,
table?
yeah.
No. Here's the deal.
Okay.
This is how equations work. Are you ready? Let me do that and then come back over here. Boom. All right. So healthcare costs. Okay. we know that healthcare costs are equal to, you see this coming up? Maybe I'll just zoom in a little bit. We know that healthcare costs are equal to, what are they equal to, y'all? Negative 3459. Yep, go ahead, Ken, I'm listening.
Plus 388.0. And then there's a symbol, I don't know how to say it.
Multiply.
Multiply, okay, multiply BMI.
Okay. We'll call
And
that
then
J5.
Okay, J5. And then plus 23594. And then the symbol again and smoking.
Multiply, yep.
Multiply.
Yep.
Okay.
Yep. Multiply by J6. And then we'll close it all up, okay? So you see that formula? All right, so let's do this. BMI, smoker. All right, a smoker is 1 for yes, 0 for no, right, in our data set. Let me get back to it. And pull that up. Here we go. So looking at it, smokers are yes is a 1, right? Okay, you ready to play in the math a little bit? I used to be a smoker. I don't know if I've told y'all that or not. I was a pack-a-day smoker for 10 years straight. So, yes, I'm a smoker. My BMI, let's just say my BMI is 45. My predicted healthcare costs are $37,595 a year. My BMI is 25 and I'm a smoker. Well, that brings down my healthcare costs a little bit, right? What if my BMI is 25 and I'm not a smoker? Let's find someone who has a BMI of 25. Look at that. And they're not a smoker. Their healthcare costs are about $3,756, right? You see this? Not too far off of 6,200, a little bit off, right? Let's find another person with a BMI of 25. That's not a smoker. They actually have really high healthcare costs. So there's always going to be that variation. If y'all get one thing out of this lecture, variation has to exist in order to make accurate or at least meaningful predictions. If we don't have variation, we don't have any variance, we have zero ability to predict. So that's one person that's 25 with high high healthcare costs and one with low. Let's find the third. We can. Thousands of people here. Here we go. Look at this. Someone else is 25 BMI, not a smoker, only $4,000 in healthcare costs. So you see how this is simply what we're doing, y'all, is we are estimating an outcome based on the predictive power of variables. And you see how I created that equation that is right here in Excel. And now what we can do is we can say, well, you know what if someone has a BMI of 50? Well, if they're not a smoker, it does double pretty much. But when they're a smoker, holy crap, it almost 1.5 times it, you know? That's the predictive power of knowing whether or not someone smokes versus their insurance charges and that sort of thing. Does that make sense to y'all? Has the world just, to use a technical term? Ken, Manta, Rajane? I don't see y'all, so I don't get the nonverbal communication I see whenever Kara's little cat friend, jumps around in the background.
I had a question when you showed the female, that 25.84 BMI. She doesn't have a children and she's a non-smoker and she has healthcare cost high. But if the same happens with a child, then the healthcare cost is low. So is it related with the number of children also?
Which one is it? This one right here, our 2584? Yeah.
Mm-hmm.
So no, so this, good question, Mamta. Look at her age.
Oh.
Oh, so look at that. There's more to
Right.
it than just the variables that we have,
Yeah.
right? Look at our male that has $21,984 in cost. You know, he's not a smoker. He doesn't have a BMI that's very high. He's only 33. But guess what? He might have other factors, right, that we didn't collect data on. There's always going to be error, y'all. You've heard me say this before. There's always going to be error. Yeah, ma'am, to your question, number of children? Yeah, because if you're going to insure, I insure myself and my wife. My wife's insurance through her work sucks, to put it bluntly. So she's under my plan. What that means is I pay more in premiums to insure both of us, right? If we had children, then we would have to pay for their insurance as well, right? That's just the run of the fact of the matter, right? If you have kids, I don't know if anybody has kids, but generally health insurance costs go up if you have children because they tend to get sick a lot, you know? So all that to say, hey, you can do exactly what I did. Look at that. I'm going to put this in the chat. You can change it from J5 to J to whatever column label you need in Excel. But that's our model. That's our model. Based on two predictors, we can explain 60% of the variation of the healthcare cost outcomes with just those two predictors. We didn't even include age, did we? We didn't include age or number of children. But guess what? We can, want to. Go look at it. Linear regression, step 2. Let's go to step 3. Include BMI, smoker, smoker recode, do that every time, and age. What do you think the R squared is going to be this time?
I think it's going to go down.
It's going to go what?
Down.
Oh, you think we're going to explain less of variance because we're adding another predictor?
Sorry, I was thinking of the difference between the R squared and that other adjusted R squared.
Oh yeah. No, we're not worried about
No.
just R squared.
Right, yeah.
By the way, yeah. Cheers. No, yeah. So what do you think is going to happen to the R squared value?
It should go up.
Should. And in fact, in any model, the more predictors we add, the more variation we should be able to explain. Even if it's just incremental increases. Go ahead, Kara.
In the book he talked about, I think, with stepwise, that's what we're doing, right? Stepwise, something. The order of the variables. Do we need to be thinking about that? Because
Yeah, no, that's a good question. So the order of the variables in which they're entered is meaningful and stepwise. And oftentimes this follows theoretical implications, right? So if we knew theory behind insurance premium costs, let's just say, then we would expect to have certain outcomes on the steps that we take that follow along with what the theory tells us is the most significant predictor, right? And in fact, we can start with whether or not someone's a smoker and then add BMI and then add age or whatever. So now what's going to happen is we're going to see if age has an impact on this model at all. Are you ready? Age on charges. What do you see right there as a correlation? age versus healthcare charges. What do we see? I'm sorry, not right here. I meant here. Age on charges. Sorry, I just realized I was circling below everything else. Age on charges. What is that? Low, right?
Low.
Less than less than 0.3, right? 0.3 to 0.5 is medium, above 0.5, 0.6 is high. There's still a low correlation, but is it statistically significant? And the answer is yes. So let's go see what happens at each step now. So before, with just BMI, again, 0.198, then we add in whether or not there's a smoker, and it brings it up to 0.658, right, as the R squared. Well, then we add age, and it goes up in almost another 10% of variance that we explained. 10% with one variable. That's pretty good. Pretty good. So yeah, adding age, now we're able to explain 75% of the variation in healthcare costs. We know that model number 3 is statistically significant because model 2 and model 1 were. Now let's go down here and look at all of our variables, all of our factors. Now the F value has changed. It's actually gone up, which is good. We expect it to go up because the predictive power of the model went up, right? If the R squared values stayed the same, then the F values would more than likely be pretty similar to each other. Under coefficients, look at that, BMI changed. It went down from 388 to 322. It's less of an important factor in the model, even though it's still highly significant. Smoker, as a recode, went up. It went up. It's more predictive now. It's a stronger predictor now that we include age. Why is that? Why is smoking a better predictor now that we've included age as a factor?
Let's assume that because as you've been smoking for longer, your healthcare outcomes are probably going to go down.
Wait, say that one more time.
As you, the longer you've been smoking, the worse your healthcare outcomes are going to, like your health, your costs are going to go up because you're going to have worse health situations.
Right. That's right. Okay. Good thought. Good thought. As if someone's already a smoker and they're older, that's going to compound the cost, right? Because your health outcomes are going to expect to be worse as you get older anyway. So if someone's an older smoker, yikes, right? That's why I quit whenever I was 28. I smoked from the age of 18 to 28, a pack a day, and I'm so glad I quit when I was 28. Just in time to meet Delaney, because she never would have dated me if I smoked. She told me that many times. So now guess what? We can add age into our model. So we've got just, this is just inputting data, right? These are all separate inputs. So we can, just make them nice and tidy little boxes that we just put stuff into. And then up here, this is what we need to change. So now our intercept is now negative 11,676. So we changed 3459 to negative 11,676. And we changed the unstandardized beta weight for BMI to 322. And we changed the beta weight for smoker recode to 23,823. And I would actually include the decimals also in a normal modeling scenario. Use as much information as we can. So let's go in and do 322.615 and 11,676.830. And then what we have to do now is simply add another predictor. And that other predictor is age. And our unstandardized beta weights for age are 259.547. And multiply it by age. Make sense, y'all? Did anybody think it would be this easy to predict an outcome? So now we need some ages. Manta, you asked about a female who had a 25 BMI and didn't smoke, and her healthcare costs were pretty expensive. Well, now that we know her age, let's add it to the model. She's 60 years old. Well, that puts her in a different class of healthcare costs. Look at that. It predicts her healthcare costs to be about $12,000. Now that's only about half of the actual value of $24,000, but at least it gets us closer, right? It gets us closer, way closer than the previous model that I think only had her at what, $3,000, I think, before we factored in age. So yeah. So let's find someone. Let's find me. Or you, however y'all want to do it. I'm 38 years old. I'm a male. I'm not a smoker, and I don't even know what my BMI is, honestly. But let's just say 38, 37, and not a smoker. Okay? So 37, 38, and not a smoker. There I am, $10,000 a year in healthcare costs. Let's see how that factors in. We overpredicted a little bit, right? 6,709 or 79, but we could also have additional males, or not males, but we could have additional people, since we aren't predicting based on gender yet. We could have additional people who are 38, have same BMI, and have higher costs for whatever reason. But nonetheless, y'all, you have officially gotten into the world of mathematical modeling. Welcome to linear regression. We are at time. I'm so sorry for carrying over 2 minutes. But it does take this much time to kind of explain and walk through these steps. And I hope this has been helpful for y'all. Okay, well, everybody, feel free to stick around if you want to. I'm gonna be here. I'll sit around for a few minutes if you want to ask any questions. But otherwise, feel free to sign off whenever you're ready. Yeah, Manta, I saw your comment. Yeah, it's simple math, right? It's y equals mx plus b plus mx plus b plus mx plus b, right? That is the linear model. Well, this has been fun, everybody. I'm going to go ahead and stop recording in case you have any more questions. Thank you again.